Hi everyone, I'm going to be working on book problem number 10.9. So it says let s sub 1 equal 1 and s sub n plus 1 equal n over n plus 1 times s sub n squared for n greater than or equal to 1. This problem has three components, so we're going to start with part A. So for part A, we want to find s sub 2, s sub 3, and s sub 4. In order to find s sub 2, we're going to plug in 1 for n, so we'll have s sub 2 equals s sub 1 plus 1. So we get 1 over 1 plus 1 times s sub 1 squared. We know from the information given that s sub 1 is 1, so we have 1 squared times 1 half, which just equals 1 half. To find s sub 3, we're going to plug in 2 for n, so we'll have s sub 3 equals s sub 2 plus 1, and we'll have 2 over 2 plus 1 times s sub 2 squared. From the previous step, we know that s sub 2 equals 1 half, so we get 1 half squared times 2 thirds. And with further simplification, we get that this equals 1/6. To get s sub 4, we're going to plug in 3 for n, so we're going to have that s sub 4 equals s sub 3 plus 1. So we have 3 over 3 plus 1 times s sub 3 squared. We know that s sub 3 is 1/6. So we have 1/6 squared times 3/4. And with further simplification, we have that it equals 1 over 48. So now we're going to be moving on to part B. So for part B, they say show that the limit of s sub n exists. We're going to do this by induction. So we're going to let P of n be the statement s sub n plus 1, which is less than s sub n for all n. We want to show that P of 1 is true. So we have that s sub 1 plus 1 is less than s sub 1. We know from part A that s sub 1 plus 1 is 1 half. So we have 1 half is less than 1, and we can see that P of 1 is true. For the induction step, we're going to assume that P of k is true. That is, P of k is s sub k plus 1, which is less than s sub k for all k. We want to show that P of k plus 1 is true such that P of k plus 1 is s sub k plus 2, which is less than s sub k plus 1. Notice that s sub k plus 2 equals s sub k plus 1 plus 1. So we're going to be plugging in k plus 1 wherever we see it. So we have k plus 1 all over k plus 1 plus 1 times s sub k plus 1 squared. And with simplification, we have k plus 1 all over k plus 2 times s sub k plus 1 squared, which is less than s sub k plus 1. So we have that s sub k plus 1 is less than s sub k for all k. Thus, if s sub 1 is greater than 0, then we have that s sub n plus 1 equals n over n plus 1 times s sub n squared, which is greater than 0. So by the principle of mathematical induction, we have the sequences decreasing and bounded below 0. So we know that it converges and has a limit. Now we're going to be moving on to part C. Part C says prove that the limit of s sub n equals 0. So from part B, we saw that the sequence was decreasing. Because the sequence is decreasing, we can say that the limit of s sub n is less than s sub 1, which equals 1. Now we will assume that the limit of s sub n equals a. This implies that a is less than 1. When the limit of s sub n equals a, we have that the subsequence's limit s sub n plus 1 converges to the exact same limit. Notice that a equals the limit of s sub n plus 1. So we have that the limit of n over n plus 1 times s sub n squared equals 1 times a squared, which just equals a squared. So we get a equals a squared. If we subtract a and put it equal to 0, we'll get that a squared minus a equals 0. By factoring, we can get a times a minus 1 equals 0. And we see that a equals 0 and a equals 1. However, we cannot include a equals 1 since we know that a is less than 1. So we have that a is equal to 0. Thus, the limit of s sub n equals 0. Thank you for watching.